All right, guys, so let's talk about reaction mechanisms and rate. And so, if you remember last year, we talked about a couple of mechanisms in particular, SN1 and SN2 mechanisms, and we are going to revisit those here in a little bit. But I need you to understand how reaction mechanisms are related to rate. And so, we're going to just do some foundation building here in this lesson, and we'll go into the actual problems next. And so let's say that you had a reaction 2A plus B plus C makes the compound A2BC. Okay, and so remember, collision theory says that for these reactant particles to react with each other, they need to do a couple of things. They need to first collide with each other, and then they need to collide with sufficient energy, and then they need to collide with proper orientation and the proper geometry or the proper spatial arrangement for the reaction to occur. Otherwise, they just bounce off of each other. And so here's the crux of this idea here, is that in this particular reaction, the odds of this being a one-step reaction, a single-step reaction, like SN2 is a one-step reaction, are astronomically high. Because for this to be a one-step reaction, you have to have two particles of A, a particle of B, and a particle of C all come together and collide at the same time with the proper orientation and the proper amount of energy. And again, the odds of that happening they're astronomical. It doesn't happen. This kind of reaction that has four reactant particles go into a single molecule, that would never, ever be a one-step process. It would always be multiple steps. And so, as a matter of fact, we could even take this example and we could cut out something. Let's cut out C and say 2A plus B makes A2B. Well, even in that scenario where we have two particles of A and one particle of B, where those three particles have to collide in the proper force orientation, those are astronomically high. That's really not going to happen either. So reactions rarely occur in single-step processes unless the number of particles that are involved are just pretty low. And so what we need to look at more often are multi-step processes. And so when you're looking at chemical reactions, oftentimes we're going to look at multi-step reactant processes. And so let's examine a possible multi-step process for this reaction. 2A plus B makes A2B. So, and what you need to be able to do here, you just need to be able to use your imagination. You need to use your imagination and come up with a two-step process. And I think once you see an example, it's going to be like, oh yeah, I can probably do that. And so an example of a two-step process of taking 2A plus B to make A2B might be that A combines with A to make A2. That would be step one. And then in step two, this A2 intermediate particle would combine with the B particle to make A2B. And so, particle A and particle A collide to make A2. Now that's one particle at this point because they're now connected. And so that one particle A2 now collides with the one particle B to make A2B. So that's a possible reaction mechanism for this generic reaction here. Let's do a second possibility. Matter of fact, what I want you to do is I want you, now that you see this, I think you can probably do it, I want you to pause the video and develop a second two-step reaction mechanism and then unpause and see if we come up with the same thing. So go ahead and do that now. And so hopefully you did a little exercise without just continuing on with the video. Another possibility is we could take one of the A particles plus the B particle to make intermediate particle AB, and then in step 2, that intermediate particle AB collides with the other A particle to make the final product A2B. And so these are two possible reaction mechanisms for this reaction. And so let's take this one step further at a conceptual level until we move into reactions, and let's identify how reaction mechanism relates to rate. And so the important thing about reaction mechanisms and rates are that the rate of a reaction always depends upon the slowest step in the reaction. And so if you can identify the slowest step in a reaction, then you have identified the rate law for that reaction, or the rate expression for the reaction. And so let's go back to, for example, earlier last year we talked about the SN1 reaction, which is a two-step process. It's a two-step reaction mechanism involving tertiary haloalkanes. So as an example, here's a tertiary haloalkane, bromoalkane, and we're going to add hydroxide to it. And so if you remember what happens, the electrons out of that bond go to the bromine. Let me go ahead and erase the hydroxyl group there. Go to the bromine, and this turns into the carbocation plus the bromide ion. And remember, there's also the hydroxide is still in here. Okay, and so that was step 1. That was step 1 of this two-step process, the formation of this carbocation. And then step 2 was the addition of the hydroxide to that carbocation to give us the final product. Now, one of these steps occurs fairly rapidly, relatively speaking, to the other, and the other is fairly slow, relatively speaking, to the other. And so this first step is actually the slow step, and this fast step, or the second step, sorry, is the faster step. And so the first step, the slow step, is the rate determining step. The slow step determines the rate of the reaction. And so let's write that down. The rate determining step. This is the slow step in the chemical reaction, is the rate determining step. The reaction will never proceed faster than the slowest step because it limits available particles for any subsequent step to react with. And so when you're looking at reaction mechanisms, if you can identify the slowest step, you have identified the rate expression. And so let's go back to our example with the 2A plus B to make A2B. So we had our two possibilities here with our mechanisms. We could have one mechanism where A plus A makes A sub 2, and then step 2, that A2 particle combines with the B particle to make A2B. And then we have another possibility where A plus B makes the intermediate particle AB, and then that intermediate particle AB collides with the other A to make A2B. Now, if I were to tell you that, hey, the rate expression for this reaction, is equal to K times the concentration of A times the concentration of B. Could you tell me which mechanism is the plausible mechanism that would occur with this reaction? Well, the rate determining step involves two particles, the A particle and the B particle. So if you're going to investigate this one over here in this first mechanism, the reactant particles are A and A. Well, that's not this because that's A and B. In the second step, it's A2 plus B. Well, that's not this either because we don't have particle A2 in here. So what that does is that eliminates this as a mechanism. There's no way that that can be our mechanism if the rate expression is equal to A times B. Rate expression is equal to A times B. It cannot be that mechanism. And so one thing it does is it helps us to identify appropriate mechanisms. So it has to be this mechanism. Not only does it have to be this mechanism, but that this expression is telling us that the first step is the slow step. The first step is the rate determining step of this reaction. And so using rate expressions and investigating mechanisms helps us to kind of really verify, because we can't see into the test tube. We can't see that A is colliding with B and then AB is colliding with A to make A2B. We can't see that. But by doing experiments and determining a rate, then that gives us clues, mental images, if you will, of, hey, this could be the mechanism. The mechanism, we believe, is going to be A hits B to make AB intermediate, and then AB intermediate collides with the other A to make the A2B particle. And so reaction mechanisms and rates, you can work very closely with those two concepts together in figuring things out. Okay, so tomorrow, or the next lesson, we'll look at some more problem-based type problems with this.